Lithium-11 and boron-19. But before going into that, I just would like to comment on helium-8 because it was some discussion, very interesting. So I just look up. Actually, I should read again this famous paper, which actually started this neutron skin definition of neutron skin. Okay. So what they measured was the interaction cross sections for helium-6, helium-8, and helium-4. Okay. And then also 2 neutron removal cross section was measured there. And what they found for helium-6, you see that 2 neutron removal cross section, 189 millibarn plus or minus 40 millibarn, is consistent with the difference between the interaction cross section for helium-6 and helium-4, which is basically consistent with each other. I mean, equivalent. This means that helium-6 is actually composed of helium-4 surrounded by 2 neutrons. So this structure is well established just by looking at this consistency of these two values. But for helium-8, interestingly, helium-8 2 neutron removal cross-section is not equal at all to the difference between the interaction cross-section between helium-8 and helium-6. This means that helium-8 is not described by helium-6 coupled to 2 neutrons. But on the other hand, if they look at 4 neutron removal cross-section plus 2 neutron removal cross-section, which is 297 plus minus 90 millibarn, which is actually equivalent to the difference between helium-8 interaction cross-section and helium-4 interaction cross-section. This actually clearly tells us that the helium-8 is made of helium-4 plus 4 neutrons. So, so this is one thing. This is very interesting, right? Helium-8 is not a 2 neutron halo nucleus, right? But 4 neutron something, 4 neutron skin or 4 neutron halo. Okay, so definition is still somewhat not definitive, but what they showed here is the theoretical calculation for the density distribution for helium-8 for proton distribution and neutron distribution, and also compared with experiment. Experiment measure means that they use this kind of information to be matched with these distributions. So this is well, if you look at this, this is not like, I mean, if it is halo, it should be like this curvature. I mean, this slope is very different for halos. Halo has longer so maybe we can call it this neutron scheme rather than neutron halos. Okay, so this is the one thing. Okay, but this paper also claims that helium-6 also neutron skin nucleus. Okay, so this is a little bit controversial with what I said yesterday. Helium-6 is neutron halo nucleus. But actually, there is some difference in the current interpretation and their interpretation. That is, okay, after this measurement, there was another measurement, that is isotope shift measurement, which can determine the proton radius, proton point radius, we call it. And if you look at this, actually, the point proton radius for helium-6, 1.72 femmeter, which was extracted from this interaction cross-section measurement, is much smaller than the value of isotope shift measurement, 2.0 femmeter. And this difference actually came from the fact that helium-6 has a di-neutron correlation, right? So as I explained yesterday. Okay, why? For helium-8, the evaluation from this interaction cross-section is consistent with this isotope shift value. This is due to the fact that, okay, so when they extract this kind of radius, interaction cross-section measurement should assume actually this kind of spherical symmetrical, how do you call it? So the 4 neutrons or 2 neutrons should distribute isotopically, okay? So that's why this is this. So I would say that since helium-6 has a di-neutron correlation and di-neutron tends to have a longer tail compared to this. So yeah, my interpretation is that helium-6 is neutron halo, while helium-8 is more like neutron skin. Okay, that's what I like to say. Okay, so by the way, maybe if you're interested in, also you should have look at this nice paper by Peter Mueller for the isotope shift measurement. So this is actually what they extracted for radii for helium-6. So this is helium-4 radius, and this is root mean square point proton radius. So it's actually larger compared to helium-4, especially for helium-6. Even for helium-8, there is some enhancement of the core. And then this is a matter radius, the total distribution. Okay. So, okay, now I'm moving to this Coulomb breakup. Well, I just would like to remind us that where are the neutron halo nucleus located in the nuclear chart. Green ones are the one neutron halo. Sorry, maybe I should start from here. Green ones are the one neutron halo nuclei, and oranges represent two neutron halo nuclei. So you see, except for helium-8 or oxygen 24, nitrogen 23, other drip line nuclei are all actually two neutron halo nuclei. It's interesting. So you see that the two neutron halo nuclei has bromine, so that you have this unbound nucleus, just one mass smaller, like this way. And for boron 19, we have these two actually unbound nuclei in between. It's interesting, similar like for fluorine. But as I said, above fluorine, a neutron drip line nuclei are still very difficult to measure. Okay, like fluorine 31 is like one count per, I would say, 1 day for something like this intensity. So we cannot measure breakup reactions and so on and so forth. So and related to the nuclear shells, so the normal magic numbers like n equal 8 is here, n equal 20 is here, but actually the n equal 20 magicity is lost. It's called island inversion region. Maybe I'll explain this. Maybe I'm not so sure if I have some slide. I think I have one slide, but later. Okay. Yes, I have one slide. Maybe tomorrow, the next lecture, I'll explain about this. Anyway, n equal 20 magicity is lost there. And n equal 8 magicity is lost in lithium-11, barium-12 region here also. Okay. So the halo structure is also kind of relevant to this shell evolution. Okay, so now I'm moving on to the soft ion excitation or Coulomb breakup experiment. So soft ion excitation is the enhanced electric dipole strength at low excitation energies. Okay, so this was also maybe discussed by Chen-san and maybe also Francesca a little bit. The question I'd like to raise here is when a nucleus absorbs a photon, what happens? Okay, for normal nuclei, like stable nuclei, when a photon is absorbed, this is dBe1 dEx means that the electric dipole strength as a function of excitation energies. And then we can see basically a peak like this, giant dipole resonance at these energies, usually, like 10 to 20 MeV in excitation energies, and which can be interpreted as a vibration between neutron fluid against proton fluid. I got this nice movie from Tom Oman, my friend. But this feature is very different for halo nuclei. So this is about the lithium-11. So when lithium-11 absorbs a photon, not only this giant dipole resonance, we see this peak just above the threshold into lithium-9 plus 2 neutrons, which is called soft dipole excitation. And I'll explain to you what is a mechanism, but basically this is related to the polarization effect due to neutron halos. But I'll explain to you through this lecture. Okay, this feature was first discussed by Ikeda-san, Kiyomi Ikeda. Actually, maybe you heard about this name because the same Ikeda-san made this famous Ikeda diagram for alpha clusters. Okay, and this, okay, this was written in Japanese, but this was from some report. It's called INS report in 1988, many years ago. Maybe most of you were not yet born, I think. But already at that time, he kind of predicted some kind of interesting electric dipole mode. Okay, so what they say is that, what he said is that this is a neutron halo-like structure. If you have a neutron halo-like structure, maybe there is some vibration between, vibration of this core against the neutron halo. That was the first idea by Ikeda-san. Okay, so then this E1 strength should have two peaks. One is giant dipole resonance, but one is the soft dipole. Okay. So, but even from the beginning, there was some discussions if this is really a resonance or not. This is really a vibrational resonance or not. Okay. So, so Ikeda model says that soft dipole occurs as a resonance of the like vibrational mode, like this one. But even without such a resonance, we may see the enhancement of the strengths. It's called direct Coulomb breakup model, okay, where the neutron halo nucleus just breaks up without forming a resonance when it absorbs a photon. Okay, but so in this case, the transition probability can be written like this: a ground state. This is a halo wave function, and then this is E1 operator, electric dipole operator, and the final state is not like a vibrational state, but just a plane wave, like final states, without any structures. Okay, but even if you calculate this, we actually, as I explain later, more detail, we actually see enhancement just above the threshold. Okay. Okay, so we'd like to know which is better, which is the most probable explanation for this excitation mode. Okay, so I have some mistake, but anyway, so what we did is a Coulomb breakup for barium-11. Okay, barium-11. So the Coulomb breakup process is nothing but a photon absorption process. Okay, so now we'd like to get the photon absorbed into this nucleus, but for the radioactive nucleus, this kind of unstable nucleus, we cannot use real photon, right? So instead of using real photon, we use virtual photon. And for that, we use this Coulomb breakup. So this is the photon absorption process, as I said. So when barium-11 actually passes by large Z target, high Z target, like that target, then the Coulomb field is like, okay, so if it is at the rest, you have the Coulomb field like this way, right? Like this way, like this way, like this way. But when first beam comes like this, then you have Lorentz contraction, so that this photon field is like really contracted to the vertical direction, like this way. Okay, so the barium-11 undergoes a pulse of strong Coulomb field when it passes by this high Z target. Okay, and then this can be translated into the absorption of a virtual photon. And it is excited, and it breaks up into barium-10 and neutron, like this. Sorry about this, another neutron, it doesn't exist here, okay? Excuse me, maybe I should. Yeah, sorry, I think yeah. Yeah, if it is barium 12, yes, we have 2 neutrons, yes. So in the experiment, we measured the momentum vectors of barium 10 and neutron. And then we can extract the invariant mass. So you know this, I think, equation. This is simple relativistic kinematics, E squared minus P squared, basically, right? So if we measure momentum vectors of these, we can also extract these energies, right? So then we can extract mass, and the difference of mass, invariant mass, which represents the mass of this excited state, minus the mass of barium 10 and mass of neutron, is called relative energy. Relative energy, okay? And basically, relative energy can be extracted. And if we know the separation energies, then we can extract also excitation energies, okay? That's the trick. And then we can use so-called equivalent photon method, where this Coulomb breakup cross-section is the product of E1 virtual photon number, NE1, and the transition probability, dBE1 dEx, okay? And this photon number can be calculated by the electromagnetic dynamics. So for instance, this is the examples of the photon spectrum. And photon spectrum has dependence on the incident energies. So if the incident energy is higher, then you can get photons at higher energies. While if you have lower energies, then the photons are more concentrated at lower energies. Okay, so especially for neutron halos, we have this soft E1 excitation. We expect some E1 strength around here, so that is actually enhanced for this because of the photon spectrum. Okay. Yes, maybe I can explain this a bit more. So I have now not only different energies now, 20 MeV per U, 67, and 500 MeV per U, as a function of excitation energies. Okay, excitation energy means that this is nothing but a photon energy, okay? And this is a kind of schematic E1 strength distribution, soft E1 excitation, giant dipole resonance. But because of this difference of photon numbers, this is logarithmic scale. So in fact, only when we have this soft E1 excitation, we can get large cross sections. Like more than 500 millibarn to 1 barn, actually. But while giant resonance becomes like 100 millibarn or even less. Okay, so even actually, sometimes we can just measure the integrated cross-section. So it's called inclusive Coulomb breakup cross-section. Inclusive Coulomb breakup cross-section already can tell us about the existence of this soft mode. Excuse me. So since then, okay, so we started this measurement around 1994. Actually, this is my PhD thesis work. And after that, we had a second experiment, 2004, for barium-11. And then we could actually determine the mechanism of this soft E1 excitation. And then later, we measured carbon-19, which is relevant to spectroscopy, because carbon-19 had a really controversial situation when we measured this. And carbon-15 for astrophysics interest, because carbon-14 neutron capture, radiative capture reaction is relevant to astrophysics, the inverse reaction, I mean. And then the neon-31, magnesium-37, we measured, in this case, we measured first inclusive cross-sections. Now we have also the exclusive cross-sections, but not yet published. But we have some publications for neon-31, magnesium-37. So anyway, this became a kind of first indication of halo structure for magnesium-37, for instance. But today, actually, I just show you, for the case of one neutron halo nuclei, I show you only one case, because for the sake of time. But you can have a look. And recently, I also wrote a kind of review, handbook of nuclear physics, so you can maybe have a look. If your library has a contract with Springer, maybe you can get freely. But but anyway. So for the barium-11, why we chose barium-11 for this study? This is because barium-11 was rather well known since many years. For instance, the separation energy was rather precisely known, 504 keV plus or minus 6 keV at that time. So this was nice. At that time, lithium-11 had a large uncertainty separation energies, for instance. And also, we knew that there is one excited bound state at 320 keV. And the famous thing is that barium-11 ground state was half plus. This was kind of a very interesting case because barium-11 we have 7 neutrons, right? So 7 neutrons means that usually it should be in P1 half neutron, right? 7th neutron. Maybe you are a theoretician, so you know these things very well, right? So 1, 2, 3, 4, 5, 6, 7. So usually, right? So normal ordering tells us that P1 half neutron. P1 half neutron. So half minus should be the ground state, but instead the upper. So you know that the upper state like 1D, 2S. Right? So this means that this guy is coming down very close to, or even inverted. So this is a very famous case, famous, very abnormal intruder state. Okay. So this was already known anyway. And then, if that's the case, barium-11 ground state can be decomposed into barium-10 plus this 2s1/2 state. But also, it should be mixed with barium-10 excited core coupled to D5/2, and so on and so forth. Okay, and already in 1979 or so, these people measure DP reaction barium-10. Okay, barium-10 itself is actually an unstable nucleus, but very long-lived. So at that time in 1970s, they had this kind of target. Now it's probably very difficult to get this. I'm not so sure how to get this unstable nuclei as a target, even though it has a very long lifetime, I know. But anyway, they could measure DP reactions to extract this component, where we call it spectroscopic factor. They got 0.77. So 77% is this component. Okay. Later, barium-11, barium-10, barium-10 1 neutron removal cross-section was measured, as I think I showed it yesterday. And they got 0.74 anyway. And barium-11 has a simple structure, 1 neutron halo structure, while lithium-11 had a 2 neutron halo structure, which is not so nice for understanding the mechanism because of the very complicated structure. Okay, so the experimental setup was like this. Okay, so the barium-11 beam comes from here, and the target is located here. We have MWPC for particle tracking, also the scintillators for the time flight starting point. And then this magnet, this is dipole magnet, so that the neutrons are just going through the magnet, and the barium-10 is bent, and the drift chamber tracks this particle and hodoscopes. And then these neutron detectors were also made. This is made of plastic scintillator walls. By the way, this magnet was designed by me when I was a PhD student. So I was allowed to designed this big magnet, which was normal magnet, but it costed like, I think, 6,000 million yen. That corresponds to 6,000 million. It's like 6 million, no, $0.6 million. Yeah. So for PhD student, it was nice yeah, to be involved in such a big project at that time. Anyway, so the result is like this. So that now we have this even strength distribution. So this is the threshold, 0.5 MeV, and we got this nice strength at very low energies. This is 1 MeV in excitation energies. And the integrated E1 strength was 1.3 E square femtometer square, which is translated into Y-scope unit. It's called 4 Y-scope unit. Okay, so usually this energy region has only 10 to the minus 3 Y-scope unit also for stable nuclei. So this was rather unusual already. So we could actually show this soft even excitation occurring in barium-11. And then we just compare this with this direct breakup mechanism, which is shown already, this matrix element, ground state, even operator, and the plane wave. Okay, and yeah, when I was a student, actually I looked up many publications and so on and so forth. And anyway, I found these equations. So if this is a plane wave, this can be analytically solved. And I also made, on the paper, I actually followed this calculation and found that this B1 is proportional to this formula, excitation energy, separation energy. So separation energy is the only parameter. That's nice. And, okay, and basically, I didn't say that, but actually this strength is inversely proportional to the separation energies. And the peak appears at 8/5 of separation energies. So peak, maybe I just write. Peak is peak. Yes, appears at 8/5. So if you write in E-rel, it is 3 or 5 SN. So this is very simple formula, and I'm very excited about this. I was very excited about this when I found it. Okay, this was the first experiment. The second experiment, we could better because we had much more statistics and published in 2004. So this is now the cross-section, Coulomb breakup cross-section, actually breakup cross-section, just breakup cross-section on lead target at 69 MeV/U, but you have two curves. The one is the angular range is wider, 0 to 6 degrees, while this is from 0 to 1.3 degrees. Why we did that, I will explain to you. But if you compare with the direct breakup mechanism model, you see the perfect agreement for this 0 to 1.3 degrees. We still have some deviation around here for the wide angular range. Anyway, since this is fitted very, very well, so we just use it to extract this B1 distribution with much better statistics and much better resolution, like this. Okay. Why we selected angles? Actually, selection angles correspond to the selection of impact parameter. This is because that actually the Coulomb breakup process is like a Rutherford scattering, but a little bit inelastic channel, and meaning that barium comes like this, and this trajectory is nothing but Rutherford trajectory, but it breaks up, it breaks up in barium-10 and neutron. But the excitation energy is anyways very small, so anyway, this trajectory just follows this Rutherford scattering. And if you know the Rutherford scattering, the impact parameter is directly related to this angles, scattering angles. This you learn undergraduate when you are an undergraduate student, I'm sure. Okay. Okay. So then, this means that we can actually plot the cross section as a function of impact parameter using this. And we did this, and you see this kind of plots. And this is interesting because this means that at large angles, large impact parameters, actually it follows like this, but then suddenly it drops. This is because that we have some nuclear absorption, right? So if the impact parameter is very small, it collides directly with target. So it is absorbed and the barium 11 is gone like this. So that's why we lose it. So this means that if we can select these regions, we are safely say that this breakup process is mainly Coulomb breakup, not a nuclear breakup. Okay. So with that, coming back to this slide, so this 0 to 1.3 degrees corresponds to the impact parameter larger than or equals to 30 femtometer. So if you select that like that, then we can safely say that the Coulomb breakup is at nearly 100%. So that's why we could use it. Yes?
The 1.3 angle is the upper or the lower? Which graph is it? The upper one and the lower one?
Which this one, this curve. This curve is for the selected angles.
The lower angle.
Lower angles meaning large impact parameter, right? According to this, right? This is like, okay, so you know cotangent, right? Okay. Okay, now, so this is what we found. So as I said, this is what we found. And now the interpretation is that this occurs due to the direct breakup. This means that in barium 11 case, we don't have a resonance, but it just breaks up. But why then we have this enhancement? This can be understood very easily. This because that matrix element is like this: ground state, halo wave function, E1 operator, and the plane wave. But this ground state has a large density distribution, large amplitude at large radius, right? Because of the halo. So actually, this is nothing but a Fourier transform of the ground state multiplied by r. This r is the distance between the core to the neutron. So that means that if you have a large amplitude at large distance, we should have a large amplitude at low q. Low q means low relative energies, like this way. So this can be understood also. Okay? And once we know this, then we realize that maybe we can use it as a spectroscopic tool for the halo state. For instance, in this case, we have this amplitude of halo state. This is C square S. The spectroscopic factor, we call it alpha squared in the previous slide. Okay, and this C square S can be extracted from this measurement, and that was 0.72, which was consistent with the previous results. Oh, yes? Okay. Okay. So, So by the way, for this final result, actually, we use distorted wave. Okay. Final result, we use distorted. But for the explanation, I often use this plane wave approximation. But plane wave approximation is actually very good, even plane wave. This is because that I think that this is because that this occurs. Okay, so this is like overlap between the halo state and P wave in outside of the potential. Okay, like this way, right? But so okay, I think I didn't bring it, but anyway. What I like to say is that since this P wave is outside of the potential, so it is not so affected by the potential itself. So the phase shift is not so large. Right. Yeah. Yeah. Maybe from P to S, maybe the phase shift is larger because S wave. Yeah. 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 I think so. Okay. Thank you. And then okay, we can also use this nice E1 sum rule. I think I think Francesca also introduced this, right? We have non-energy weighted sum rule. For instance, you can have a look at this S. Benson's paper. So if you integrate over B over V1, then this integration is written like this. So if you sum up all the final states, right? You can sum up all the final states, then this becomes one unity. So you can write like this, R squared. So this becomes an expectation value for R squared. So actually, one can use this E1 strength, which was like this. And then we can extract R squared between the core to the neutron. So we extracted this value as 5.77 femmeter. Yes. So this is nice, no? It's very huge. So it's actually the size is, this size is more than twice the core size, actually. Okay, so it's nice. Yes, and I just said that here ZE over A is related to so-called E1 effective charge. So E1 effective charge is nothing but actually the charge. This is ZE, right? ZE. And then this distance between the charge center of mass and the center of mass itself. Okay. So this is this is R over A, right? In the case of one neutron halo nucleus, 1 over A. So that means that if you multiply the charge times this distance, then this becomes ZE over A R. So this is nothing but the effective charge for electric dipole. So it comes here, ZE over A, okay? Yes. Okay, so this is a kind of interim summary for Coulomb breakup one neutron halo nuclei. Okay, so yes, we have two publications, and the Coulomb breakup is a powerful method to probe soft E1 excitation, and soft E1 excitation for one neutron halo nuclei have been found to occur due to direct breakup mechanism and not soft dipole resonance. And yes, we have some following publications, so you may want to have a look. Okay, that's it. And then now I move to two neutron halo nuclei. This is more challenging, but maybe more interesting. Okay, so helium-6, there is a very nice pioneering work by Tom Orman, but we have also recent publications from RIKEN data and lithium-11, boron-19, carbon-22. Okay, so today I talk about lithium-11 and boron-19. And in the workshop next week, I'd like to show you some results on carbon-22, but not today. So hope you can also join this. I'm not so sure. Yeah, some of them. Okay. Yeah, if you don't attend this, and if you want to see, I can show you later in the break. Okay. Okay, so one neutron halo versus two neutron halo. So one neutron halo is like this, two neutron halo is like this, lithium-11. But we know that basically, for one neutron halo, we have this motion between core to the neutron, as we saw. But for lithium-11, we have core to the neutron, core and first neutron, core to the second neutron, or two valence neutrons. So there are more degrees of freedom. Sorry, I need water again. So the Coulomb breakup of lithium-11 were rather controversial in 1990s. There were 3 experiments. One is from GSI, which measured Coulomb breakup of lithium-11 at 280 MeV per nucleon. And this is the lead target data, and this is carbon target data, okay? And then this is from MSU, Michigan State, 28 MeV per nucleon, low energies. And they showed this Coulomb breakup cross-section as a function of excitation energies. So this is 0 to 1.5 MeV. This is logarithmic scale, okay? And then there's RIKEN data at 43 MeV per nucleon. And okay, this is the Coulomb breakup cross-section, and this is the threshold energy. So this is the excitation energy again. Maybe if you look at these three figures, you don't know how these are consistent or inconsistent or whatever. This is because that photon numbers actually have dependence on the incident energies. So to compare, we should actually compare by dBE1 dEx. Okay? So we did it. So this is the result. So summary of the previous experiments of lithium-11. So actually, it was rather controversial with each other. Okay, so this is MSU data, 28 MeV per nucleon. So this is like this. And then the Zinza et al., GSI, dashed lines. So they have some kind of area where the experimental values are consistent. So they say two bumps, which should be within these error bands. And then the RIKEN data is shown by this histogram. Okay. Maybe if you look at this, maybe RIKEN data is rather close to Zinza et al., GSI, but not quite. So anyway, we needed to measure again with higher statistics. Basically, the setup is very similar to this barium-11 case. So at the time, we used RIPS fragment separator at RIKEN, the former fragment separator. And we used lithium-11 at 70 MeV per nucleon impinged on lead target. We also had DALI, already the gamma ray detectors surrounding the target. And then this magnet, which was designed by me during PhD thesis. And then we measure lithium-9 and 2 neutrons. Okay. And okay, here, you are basically theoreticians, experimentalists. No experimentalists. Okay, do you know how to measure neutrons? No? No idea? Okay, scintillator, we use scintillators. So the scintillators, maybe I can just show you here. So we have scintillators, right? Scintillators. Plastic scintillators, actually plastic scintillators. Are made of basically carbon and hydrogen. Okay, so if the neutron comes, neutron is neutral electrically. So basically, well, most of the time actually it goes through, right? But in some probability, it can collide with proton from hydrogen, right? Then proton is like this, and the neutron goes like this. Okay? If proton is recoiled, then proton emits signals in the scintillator. And once, plastic scintillator is basically excited, so that light is emitted. Light is emitted like this, and maybe like this, right? And then this light is transmitted to the photomultiplier tube. Maybe you know photomultiplier tube, right? Okay, so maybe you did this in the laboratory in the undergrad course. Okay, so now we know that if you see the signal here and here, okay, then we know that neutron comes. Neutron was here. Okay. Okay, even for carbon, we have signals. This is because within this carbon nucleus, we have 6 protons. And one of the protons can be knocked out. This is quasi-free scattering we discussed yesterday. So this is the way. But then, 2 neutrons, okay? Okay, so now we have 1 neutron coming here, okay? And then this is plastic scintillator. Okay, as I said, the neutron can scattered like this, okay? Neutron can be scattered like this. Protons are recoiled here, okay? But then this neutron can also make another proton here, right? So this means that from one neutron, maybe we have 2 signals. And then if we have 2 neutrons, and independently, if they produce signals here and here, then 2 neutrons can produce 2 signals. How do you distinguish this 1 neutron from 2 neutrons? It's not so simple. Please understand, theoreticians, how difficult to measure neutrons, right? Especially multineutrons. Okay, so then what we did is actually we used the information timing here and timing here. We have register time 1, time 2. So then we just assume that this was 1 neutron, and then we can measure the velocity here, beta 1 and beta 1, 2, okay? And then what we did, impose the condition that beta 1 should be smaller or equals to beta 1, 2. This shouldn't be scattering, because if this is a scattered neutron, the velocity should be lower than this velocity, right? So if this kind of thing happens, this is not from the 1 neutron scattered, but 2 neutrons hitting independently to these 2 scintillators. And this kind of thing can be done when 2 plastic scintillators are separately installed. And we did it because we knew that this can be used. So, and also, this is also a kind of detail, because I think theoreticians, lecturers, explain a lot of equations. I think I should explain about the experiment more, I think. So the gamma rays, also sometimes this can emit gamma rays from here, because carbon can be excited to the the 2+ state, which can emit gamma rays. And this is a kind of annoying background, so I just set the so-called threshold, 6 MeV EE. Maybe you don't know what does it mean. EE means electron equivalent. Okay, so maybe I can explain later, but anyway, with this, we can avoid the gamma ray from carbon target. And with that, we could this efficiency curve as a function of 3-body relative energies of lithium 9 plus 2 neutrons. So this is our evaluated acceptance or efficiency. While GSI experiment uses just a big chunk of plastic scintillators plus ion thing, so that they couldn't measure lower relative energies. You see that if there is only one chunk of plastic scintillator and these 2 neutrons are very close to each other, okay, you cannot distinguish these 2 neutrons, right? So if the 2 neutrons are very close to each other, the relative energies become small, right? So then that's why Zinza et al. Doesn't have any sensitivity at very low energies. While MSU actually used similar technique, so that they had some nice sensitivity at low energies. Okay, with that, what happened? So this is our result, black dots. And our results are rather similar to actually the MSU result, okay? This is due to the fact that we have much sensitivity compared to the previous experiments of RIKEN and GSI, okay? Okay. And okay, maybe, as I said, maybe I should explain how difficult experimentalists are working, okay? How hard we are working. Okay, so this is from my notebook, 2005, 20 years ago. Okay, so of course, now we found that our experiment results are not consistent with previous results. Do you think I can publish immediately? No. I should investigate why this happened, right? So what I did is that like this. So this is, again, the Coulomb, okay, breakup cross-section as a function, three-body relative energies. And this dotted curve is the before any selections. Okay, so this is original curve. Okay, and then I just artificially select the neutron-neutron relative energies, which should be 300 larger than 300 keV. This means that we just mimic the situation of GSI. Okay, GSI didn't have any sensitivities below 300 keV, two neutron relative energies. So I just selected this large neutron-neutron relative energies. Then this curve becomes like this. Okay, and then also the energy is different. We used 69 MeV per nucleon, and they used 280 MeV nucleon. So we needed to calibrate for this photon spectrum. So we just evaluated that, and this becomes like this histogram here. And then this cross points, this is Zinza et al., GSI. So you see, now we are consistent with each other. Perfect. So and then I realized that, okay, now I understand everything. So now I can publish in PRL. That's it. Yeah. So do you think you want to be an experimentalist? Okay. Okay. Okay, anyway, I move. Okay, so we can also use this non-energy weighted cluster sum rule again. But in this case, this R square is between core to these two neutrons, center of mass, this R. And this R is also can be related to the R1, this vector, and this R2 vector. Okay. So we have now the component of R1 dot R2, the dot product. So now I thought that maybe we can use it to extract some correlation between these two vectors, R1 dot R2. Okay, so I did it. So this is the same thing written. And then, okay, we had some distribution up to 3 MeV, but we extrapolated to actually larger energies using this, using some calculation, theories actually. And then we extrapolate like 1.78 E square, penta square. And then we evaluate this opening angle to be 48 degrees. And later, Carlos and Mahir from Brazil, actually he was from Brazil, estimated 66 degrees, or Hagino-san, Sagawa-san extracted 56 degrees. So now we know that there is some neutron-neutron correlation. So this is one of the first evidence for this dineutron correlation of the lithium-11. So this is, we can say that soft ion excitation of two neutron halo nucleus can be used to extract the dineutron correlation. Hi?
So here both is R1 and opening angles are unknown, right? So how do you determine two numbers?
Yeah, that's a good question, actually. So we couldn't extract theta 1, 2 immediately. So we also extract the non-correlated BE1, for which we used the theory of Espensen. So compared with the non-correlated E1 strengths, we extracted this value. So this assumed that. While Beltrani-Hussein actually used a reaction cross-section as another input, I think Hagino-san also did it like this. So if you use a reaction cross-section, then only from experimental two values, we could extract these values. Yeah, you're right. And now we are using this kind of thing, yes. So, okay, so dineutron correlation is, okay, so this is from, this is a slide from Hagino-san, the theoretician. So he explained like this. So the, I explained actually already that parity mixture is very important. So, so this is the calculation for when parity is not mixed, but when parity is mixed, then there are some polarization occurs like this. And in the case of lithium-11, they calculated like there are two bumps anyway. This is due to the P wave. This is due to the P wave. component, but this dineutron part has more probability than this Siga type, so-called Siga type contribution. They found it. So if you take the average, it becomes like 60 degrees, actually. Okay. So this was already explained yesterday, so I just skip. Okay, I did it. So just for your reminder. Yes. And then as I said, this is called dineutron. Dineutron means that theta 1, 2 is smaller than 90 degrees, but there is another correlation called Siga-like correlation, which is like this, over 90 degrees. So as I said, in reality, we have both correlation, like this, dineutron and Siga-like, but dineutron usually wins over Siga-like correlation. Okay. One remark about this S and P wave mixture. So you wonder why in lithium-11, S and P are mixed, almost equal. So there is one explanation which was proposed by Mio-san in this paper. Okay. So you can just imagine first the lithium-9 configuration. The lowest configuration is PS1 half filled, P3 half filled, like this. Okay. But usually there is a kind of pairing correlation where you have a component, two particles, two neutrons are excited to P1 half like this. Okay. And also there is a tensor correlation, so-called, where the one proton, one neutron in 1s orbital, the lowest orbital, goes to P1 half like this. Okay. So by mixing these two, the lithium-9 gets correlation energy, so it becomes more stable. Okay. How about lithium-11 case? If you want to add, if the lithium-11 is pure P squared, okay, assuming like this way, okay. If you add two neutrons here, it's okay. But if you want to add two neutrons here for this pairing correlation, you cannot because of Pauli blocking, and also you cannot do it for tensor correlated configuration, right? So this means that this is not favored, or energy is lost. While if the 1s1 half orbital is added, this is fine, but this is fine, and this is fine, because 1s half orbital was all empty anyway from the beginning. So this means that S squared configuration has energy gain. Okay, so that's why this is going up and this is going down. So it is almost degenerate. That's the situation of lithium-11, well, according to this paper. This is interesting, I think. Okay, I think I have still some time, right? 15 minutes, yeah. Just a moment for water. Now I'd like to discuss boron-19. So boron-19 is located here. This was published nearly 5 years ago, actually. On the neutron drip line, we have boron-19. Okay. So okay, we discussed this, I think, but the question is what happens when neutron drops are introduced in the nucleus? So this was discussed, I think, yesterday, but we have now 4 neutrons. What happens what happens when 4 neutrons are in the nucleus? Okay, so we discussed this dineutron. Lithium-11 has dineutron. But recently, barium-16 2-neutron unbound state has been found to have a dineutron correlation. You can have a look at this paper. And then we are now, we would like to also measure oxygen-26, which was already known as a very weakly unbound nucleus, only 18 keV above the 2-neutron decay threshold, we know. So we would like to measure it, but due to the stop of calcium-48 beam at RIBF, we cannot go further, unfortunately. But Hagino Sagawa actually predicted a very large, probability for this dineutron correlation for this nucleus. So we'd like to see it. How about 4-neutron? Okay, we discussed helium-8 today and yesterday, and this is very interesting. Okay, maybe Hiyama-san would like, prefers this dineutron picture, I think. But maybe 4-neutron correlated like this, I don't know. And boron-19 is also an interesting case for 4-neutron correlation because 4-neutron separation energy is very small, 1.47 MeV. And the 2-neutron separation energy is also small, 0.089 MeV. Yes? Oh, I'm sorry. sorry. This was my mistake. Yeah, maybe I should. Sorry about this. This is very strange nucleus. Okay. Okay, and then we discuss in the next lecture. We would like to discuss oxygen 28, which is unbound, but oxygen 24 is rather established doubly magic nucleus. So maybe we have 4-neutron correlation. Okay, so about boron-19, there's a discussion if boron-19 has a 2-neutron halo nucleus because 2-neutron separation energy is very small. And also the last 2 neutron may reside in S1/2 orbital like this. While boron-19 can be 4-neutron skin, especially 4 neutrons are in D5/2 orbitals like this. So, this is a kind of question, I would say. And maybe I just would remind you that the S-wave favors halo structure because of no centrifugal barrier. Okay? And the experiment was done at RIBF. I think I don't need to explain this again. We used Samurai facility here. And in Samurai facility now, so you saw this smaller magnet which I built in a PhD thesis, but now we have this big magnet. This is a Samurai magnet, 3 Tesla superconducting magnet, 600 tons, 10 times heavier than what we used in the previous experiment, actually. And then, in this case, boron-19 beam was produced from RIBF fragment separator and impinged on the lead target located here. Okay, and then after excitation, it breaks up into boron-17 and 2 neutrons. So boron-17 was bent by a dipole magnet. We have now big drift chamber, 2 drift chambers and photoscope, and 2 neutrons are just going into nebula, a new neutron detector based on plastic scintillators, okay, like this. So we used a similar technique to distinguish 2 neutrons. So I'd like to show you first the inclusive cross-section. Inclusive means that we didn't impose a condition that neutrons are measured. Okay, so we just measured boron-17 in the outgoing. This is exclusive. Okay, this is inclusive. Okay, inclusive means that we didn't impose any conditions on the neutron detections, so that we just measured boron-17 out of boron-19, which was 1.8 bonds, which is very, very large. And for carbon target, we got 0.25 bond, 250 millibonds. Okay, so if you look at the ratio of this lead target to carbon target, it was 7 times. Okay, and if you even measure 2 neutrons in coincidence, this is exclusive, we call it, and then the cross section is a bit smaller, but the ratio of carbon to lead becomes 22 times. Okay, we also saw 4 neutron removal cross sections, inclusive, meaning we didn't impose a condition of neutron detections. Then we got 600 millibonds for lead target, 485 millibonds for carbon target, and the ratio becomes even smaller, 3.3. And 3.3 is like a nominal value even for the stable nuclei. The nuclear breakup into carbon target to lead target, even if you assume the breakup cross-section for red target is basically nuclear breakup. So this means that for 4 neutrons, nuclear breakup is dominant, and for 2 neutron removal, Coulomb breakup is dominant. This already showed that actually the beryllium boron 19 is more like boron 17 plus 2 neutron, but not boron 15 plus 4 neutron. So, okay, so this may be related to this another paper, which was also from our collaboration about boron 16, which showed that boron 17 neutron has a D wave dominant, is a D wave dominant, meaning that boron 17 is not like very good halos. So maybe boron 17 is a rather good core in boron 19. Okay, coming to the cross sections. This is Coulomb breakup cross sections as a function of relative energies. Okay, we plotted here the logarithmic scale. So this means that we have a very big enhancement at very low relative energies around 0.3 to 0.5 MeV. Okay, and compared with many theories actually. First of all, we said that the adopted 2 neutron separation energy is 0.085, or I mean 0.089 MeV or something, 89 kV or something. But this cannot reproduce at all our data. Okay, so we just changed the separation energy a little bit higher to 0.5 MeV, and then we got very nice result, nice consistency like this. Okay, if we don't include the S-wave component, then the cross-section becomes even lower like this. So S-wave is significantly included in boron 19. That's one thing. And if you don't have no dineutron, then the curve becomes very different. So we concluded also dineutron contributes to this cross-section. So this is a summary of what we saw. By the way, maybe I should also tell you that BOV1, after dividing by this photon number, we got BOV1 as a function of relative energies, and this is the experiment points. We also compared also the scattering lengths between boron 17 neutron, minus 50 femtometer of minus 100 femtometer, and then, well, we cannot distinguish, but at least scattering length amplitude is very large. That is sure. So to summarize, this is a summary. So we got large E1 strength, 1.6 E square pentameter square, which is actually very close to lithium-11. This is signature of halo. And core 2 neutron distance was also extracted using the sum rule, 5.75 femtometer, so which is very large. Separation energy should be close to 0.5 MeV, and significant S-wave component will develop dineutron correlation. And this is consistent with large scattering lengths. Large means that the amplitude-wise, so the A should be smaller than minus 50 femtometer. And since 2 neutron, I mean the Coulomb breakup cross-section is dominated by these 2 neutron removal channels, 2 neutron halo is dominant, but not for 4 neutron scheme. Okay. So this is the conclusion. And also, we compared with the theories which reproduce our data, well, 3-body model by Hagino-san. So this model shows like this. So now we have 3 bumps. This is due to the D-wave component. But this dineutron component is the largest, enhanced in probability at theta 1, 2, opening angles 25 degrees. And looks like this, we have this 6% negative parity component. Even with 6% negative parity component gives this large enhancement of dineutron correlation. And this asymmetry is actually caused by this negative parity mixture that is found for this theoretical calculation. Okay, so this is a summary of this 2 neutron part. I think I don't need to repeat. Okay. Yes. So how many minutes? Maybe 5. Okay. Maybe I can just discuss a little bit about this soft E1 excitation. So we discussed that the soft dipole excitation is resonance or not, right? And we can be sure that one neutron halo nuclei, basically this is caused by direct breakup mechanism, not a resonance. And for two neutron halo nuclei, most likely direct breakup, but sometimes affected by strong finite state interactions. And for two neutron halo nuclei, resonance possibility is not fully excluded, I would say. And so, and about soft resonance, actually, there is another experiment by PP prime or DD prime reactions by Tanaka-san or Kanugo-san. You can have a look at this literature. But they actually found some resonance state in lithium-11. But this resonance state may be may be different from what we saw in this direct breakup. So maybe in the Coulomb breakup, maybe direct breakup may dominate. But if you use a light target like this, maybe you can excite resonance-like structure in lithium-11. So also, I just would like to remind you about pygmy mode. Okay, pygmy mode was discussed by Francesca, I think. Okay, so or maybe Ingo also. Maybe you discussed pygmy. No. Okay, sorry. Okay, sorry. So if you look at the density distribution for stable nucleus, neutron skin nucleus, neutron halo nucleus, so you can see that the neutron skin nucleus has some extra neutron distribution over protons like this. Okay, but basically this profile is similar. Okay, but for neutron halo nucleus, we have extra distribution which has different slope like this. And what happens is that for this case, we have GDR, giant dipole resonance. For this case, there is, so this pygmy dipole resonance is believed to be actually vibration between this neutron skin against this proton core. So it should have this kind of small peak around 5 to 10 MeV. So this is related to neutron skin physics. And for the neutron halos, we have this another mode due to this distribution. This is soft E1, maybe we call it. So please distinguish these two. Sometimes people are mixed with each other. Sometimes people call PDR for soft E1. So maybe we should be careful. That's it. So thank you very much for this part.
Thank you very much for the nice talk. So you have any question?
So in this slide, the last neutron halo case, there is 3 peaks also. So there is a pygmy dipole resonance, and on top of that, the soft.
Yeah, I think, okay, so far, our measurement can measure up to, I would say, like 6 MeV or something. So from 0 to 6 MeV, we didn't see this pygmy. So this is kind of expectation, a perspective, I would say. But if we can measure, actually, this is one of the projects for the future project. We should actually measure not only this low energy peak, but also high energy peak, including pygmy dipole. But for that, I explained that we need higher energies. Maybe I think this FAIR facility may be better because the photon energy for the higher excited states can be obtained when you have higher incident energies. Okay?
I mean, more or less, the nature of both processes are the same, I guess.
No, as I said, the neutron halo case, we see this because of the kind of direct breakup mechanism, where this is like, so we call it, this happens because of the this matrix element I showed. Okay, so I think this can be explained by this one neutron halo nucleus here, or maybe a little bit later. Yeah, here. So basically, what happens is that if we have this large density distribution, okay, this can be easily coupled with wave at large distance. And large distance means long wavelengths, right? Long wavelengths means low energies. Okay, so that's why we have a low energy peak like this. And this can happen without forming a resonance. Okay, so this is not a resonance, but rather kind of coupling of the ground state and the final state. And this happens because of the kind of polarization effect in a sense, because neutrons are center mass is shifted from the core, the charge center, right? In the case of neutron halo nucleus. So that causes this kind of effect.
Okay.
But for pygmy, still, I think people believe that it is due to the vibrational mode, I think.
Okay.
Any other question?
So about the Brilliant 11, so because I think Tobias already mentioned there's a P-wave state, right? So if there goes through S to P-wave transitions, does this appear in the measurement in the breakup?
Yes. So the you mean the breakup process?
Yeah.
Yeah. So breakup process occurs like ground state and the plane wave, but plane waves, of course, decompose into partial waves, right?
Mm-hmm.
And of course, because this is E1, the final state is just L equals to 1.
But this
wave.
P-wave bound state doesn't appear
Okay,
here,
there
right?
is also, yeah, okay, you mean the bound state.
Right.
Okay, but if it goes to bound state, the final state becomes barium 11.
Mm-hmm.
So it's not the breakups.
Yeah.
And this was also measured. This E1 strength was also measured in different experiments. Actually, we measured also. We have some publication. And it is like 0. I think it was like, I think 0.1 e square pentameter square or something. 10%. So it's not so large, but it's large in a sense that we don't have strengths at this region usually, right? Okay. So this is the bound. So in a sense, we have the strengths here also. Right. 0.3 MeV. Yeah, strengths here. It's like 10% of this strength. Mm-hmm. Yes.
And okay, so following up question. So for this incoming beam, can it also have this P-wave bound state inside?
No.
No. Okay.
This is because at the so this excited state has very short lifetime. Okay, this is not isomer. I think femtosecond or something. So even if it is excited, it just goes down. Yeah.
You were talking boron 19?
No, barium 11. Yeah, barium 11 has a first excited state.
Yes. 1.5
Yeah,
state.
I think I showed this somewhere here. Yes. He talked about this state, right? Yeah, and so this state is also E1. This can be also excited by E1, yeah, electric dipole, and we measured also. But in this case, it doesn't break up. Yeah, and he wonders also this can be mixed in the beam, and it is not.
I've got a follow-up question, like to the DB1DE slide, like the slide 17. So basically here, so if you do like a E1 translation, like from S wave to, because you measure like till like 4 MeV more or less, like in relative energy, right? And if you look at the beryllium 11 spectrum, like there is like a 3.5- resonance somewhere. So if you, let's say that instead of putting like plane wave in the bra, you put like Coulomb waves, right? Like Coulomb, I mean like with final state interaction, you have a contribution from the P wave bound state, and then a contribution from the resonance, like the 3.5-. And so that one is dominant, and then the one coming from the bound state is...
Maybe I'm not so sure if I follow your question. So you think that there is another state?
So maybe like can you put like the formula?
Formula.
Yeah.
Okay, sorry.
Yeah, that
Yeah.
one. So if you do like an E1 translation like from a S wave, you will
Yes.
have contribution like you have like P waves continuum, right?
Right.
And so let's say that you want to include like final state interactions.
Right.
So you have like the P wave bound state that you showed, like bound state.
No.
P wave
Okay.
continuum. I mean.
No.
Like-
It's still scattering state. It's still
Yeah, like
scattering state.
Scattering state, but like 1/2 minus.
Yes, 1/2
scattering-
minus
Yeah.
or 3/2 minus
3/2
maybe.
minus.
Yeah.
And so like the 3/2 minus will be dominant. So,
We didn't analyze like that.
so we may like
in
we
this
made-
case, I think it's 1/2. Both are included, I think. Yeah.
both included, but I
I
think
think.
the 3/2 minus is the. And so I had a question about like the spectroscopic factor here because like this spectroscopic factor is not an observable. Like for example, you take it from transfer reactions,
Right.
and then you put a number like maybe 0.72.
Mhm.
But like I was wondering, because like ab initio people like they said okay that there's like a 0.9 spectroscopic factor,
Uh-huh.
and so like they overestimate like the dB1 and then the Coulomb breakup cross section. So I was wondering like if the dB1D is unobservable, if the spectroscopic factor is not unobservable, like how do you make sure that things are consistent?
So you're talking about the So this is This is more like actually a ANC in a sense.
Yeah.
Yeah. So So to extract the spectroscopic factor, we of course need to assume the wave function.
Yeah.
Yeah.
And it's normalized
Yeah.
to 1 because that's a 1-2 body type of
Yeah.
stuff.
But in a sense, this overlap. I mean, this wave function. I mean, this matrix element. Compared with this matrix element, we got this kind of factor, right?
Mhm.
Some kind of overlap.
Yeah.
Yeah. So this is maybe we can call it ANC, but from ANC we can extract this spectroscopic factor when we assume the wave function.
Yeah, obviously. Okay.
Maybe
okay.
that's a more
So it's-
precise way.
It is not unique, right? So it's model dependent.
Well,
Was-
yeah, but more or less we have some kind of standard wave function
Okay.
for this 2s1/2. So maybe
okay.
not so, maybe 10%
Okay.
accuracy, I would say, depending on the model.
Okay. Then I had another question about like when you show this formula with the equivalent photon method,
Right.
and you show like the result like when with the two.
Like this. Sorry.
Yes, that one, and then like you show the results like with the cross sections of beryllium 11 on lead with two different like angle ranges. With this formula, you showed like the cross sections beryllium 11 on lead for two like small scattering angles.
Okay.
And large,
I see.
Yeah.
Like this one.
And
Yes.
so I think if I remember, like the paper, like the smaller, like you did the calculation for large impact parameters,
Right.
so small scattering angles, but like the other curve, like I was wondering, like how do you pick the impact parameter because like it's larger, so that means like there will be more nuclear contribution, right?
Right.
And so I was wondering, like how do you pick, like the impact parameter because you're less sure you have to go
Okay.
beyond
So
the.
So in that case, we should assume the impact parameter so-called cut
Yeah,
the cut
yeah.
of impact parameter. I think we use 12.3 femmeter or something, 12 femmeter or something.
Like to what does it correspond? Like
So I think, for instance, I showed here this kind of curve.
yeah,
So from this, we can actually estimate somehow a cut
Yeah.
of
because
parameter.
I tried to make a calculation where like if you look at the curve here, let's say you take like 15, and if you put like as a impact parameter, for example, let's say you take 15,
You see here.
yeah,
Yes.
and you make
But
a
maybe the cut is, I would say this is also due to some, well, it's difficult to say if this is here or here, but I think I just take the half,
yeah. Because I was
of the
wondering, like,
peak.
if you look at because it's very steep, so if I do a small change in the impact parameter,
Mhm.
like the number of virtual photons, like it changes a lot sometimes. Because like it goes down, like,
Okay, but I mean, once you have some consistencies with the data, I think this is rather well defined.
okay. And then maybe a last question, like,
Mhm.
I was wondering, like, why don't you measure sometimes like the dBE2 DE, for example, like
E2.
E2, yeah, like for
Ah, okay.
example, to see the influence of like a S to D
Aha,
continuum.
I see. Okay, so in the case of halo nuclei, actually E1 is dominant. That is due to this fact of this effective charge. Okay, so where did I? Maybe this way. Effective charge. You know that it is. Yeah. So this effective charge for E1 is much larger than E2 effective charge in the case of halo nucleus. This is because that in the case of halo nucleus, the center of mass is shifted from the center of mass of charge. So that's why E1 is very large. Okay, and then E2, I think it's like 1% of the E1 in this case.
Yeah, I asked that because like I think in the same like you show like for example there's when you do like beryllium 11 on carbon, you see that there are those peaks like corresponding like to the D resonances.
Right. Yeah.
So I was wondering if there was a way to compute like a dB2 DE that shows the influence
Okay,
of those.
I see. It's difficult for carbon target because carbon target is dominated by nuclear breakup, right? So to extract VOV2, maybe we can extract so-called delta deformation parameter. Yeah, but dBDE we cannot. dBE2DE, yeah.
But so the 2+ state is a resonance state, right? 2+ state is resonance state. Yes, right? Am I correct? Yeah. Resonance state for the 2+ state.
Yeah, so we could measure this, yes, but with carbon target. But extracting VOV2 is very difficult. Yes. Okay.
Could you go back to the last slide again, where you have
Yes.
shown the difference between neutron skin and halos?
Yes.
Thank you. So I'm still trying to figure out the difference. So the difference here you see with the soft E1 structure that if you have a neutron halo, you have like this imbalance of the center of mass and center of charge, which leads to the structure. So could one maybe say if you have, for example, a 2 neutron halo and they have some strong d-neutron correlations, then again you get an imbalance and you get maybe a similar structure. And for 4 neutron halos, like maybe helium-8, is it then the same? So like the measure could be the correlations to say or to distinguish between neutron skin and neutron halo. So strong correlations would speak for a halo and weak correlations for neutron skin. Could that be some measure for it?
Maybe I didn't get the point. So in the case of 4 neutron?
Yeah, like we could just calculate if there are strong correlations or not between the neutrons. And if there are strong correlations, that would correspond to a halo, or otherwise, if there are weak correlations to a neutron skin, could that be like the difference? Or
Maybe I don't get what you mean.
yeah, like we had here this breakup of the soft E1 structure, which happens if you have correlations or if you have like this imbalance of charge.
Okay, maybe so even for 4 neutrons, if we have this kind of correlations, I don't know if this happens. Maybe it's very difficult. You mean this kind of correlation?
Yeah, in a very extreme
yeah,
way.
in
Then
this
that,
extreme case, then we may see soft event. Yes, this
Okay.
may see this kind of even strength because the charge is shifted from the center of mass.
Exactly.
But
And what I mean is like, I mean, that's very extreme if
Yes.
that would happen, but you could also have like 2D neutrons which are in some angle and then also have some slight shift of the charge center of mass and like that. And these correlations could speak for being a halo instead of a skin, or other way around then. So I'm trying to figure out
well,
what.
yeah. Well, anyway, we don't know how this is correlated, so we cannot say easily. But one thing is that for instance, in the case of helium-8 or boron-19, I think, well, helium-8 case, for instance, I think this is not the case anyway, right? And maybe if we can really see that this dependence, I mean, density profile, if we can see the density profile is similar to protons, maybe we can call it neutron skin, like this. But the neutron halo is due to this tunneling effect, basically. Like when the separation is smaller, then you have large density distribution outside of a potential. If that happens, we can call it halo, I would say.
Okay.
So yeah, maybe we can discuss.
Yeah, I think
further.
so too.
Yeah. Yes, we have another session. So yeah.
Thank you.
Okay, any other question? Okay, Francisco.
So I have a question also related to helium-8. I imagine you are familiar with the RIKEN data. So how do we relate what we see there? There is like a peak at around 2-3 MeV with this picture.
Okay, so actually, Tom didn't show me very much.
Okay.
So maybe I
like
should.
maybe we can do this offline.
Yeah, maybe we can do this offline.
Yeah.
But if this, okay, so now the 4 neutrons are maybe distributed like isotropically, right?
Mm-hmm.
So then this means that maybe this is, if I don't see that data, I should say that this is due to pygmy dipole.
Okay.
Rather
we
than
can
rather
discuss
than
later, no
yeah,
problem.
soft dipole maybe. But we should discuss later. Yeah.
Okay. Any other question? No? Okay, so then also it's time. So thank you very much for the second lecture. Okay, so next and the session will start at 11:15. Is okay? Yes, we can have some half an hour in the break.